Greetings everyone, welcome to my video again, and we are going to continue Mtcna Module 3. In today's video we are going to talk about networking models, and there is some subtopics. There is concept, TCP/IP model, encapsulation and decapsulation, and then there is C model, layer model. For the concept, it's the concept of the networking models. So let's just get straight into it. Just prepare yourself. It's going to be long. It's gonna be very long explanation. So be prepared. So the concept of a networking model is a set of guidelines and standards that defines how data is transmitted and received over a network. It's also known as a networking architecture or a networking blueprint. It also provides a common framework for networking devices and software to communicate with each other. It is a comprehensive set of documents. Individually, each document explains a single function required for a computer network. Collectively, these documents describe how a computer should work or exchange data. Some documents explain the physical requirements for a network device. For example, a document could describe the current levels and voltage used by a specific cable to transmit data. Some documents describe protocols. A protocol is a set of logical rules that devices must follow to transmit data or communicate. A networking model is similar to an architectural blueprint of a building. We use an architectural blueprint for a building to ensure that the building has the correct hidden space to accommodate the electrical, plumbing, gas, and other secretive amenities, and has the right structure and foundation so that it remains standing for many years. We also share the same blueprint with contractors, masonmen, painters, electricians, plumbers, and other workers, so their part of the work do not cause problems for the other co-workers. Similar to it, administrators use networking models to build their networks. Although they can build their own networking model, they use an already built networking model. If they use their own networking model, they have to develop their own software and protocol and build their own networking devices and networking cables. But if they use an already built networking model, they can purchase networking devices from the networking product vendors who build their product for the same networking model. Since the products are built for the same networking model, they work well. So there is before there is networking models or open networking models. It's from the pre-1980s. So before 1980s, there's no standard models existed. So computer networking was characterized by vendor-specific architectures and proprietary protocols. So there's more turn-offs with before 1980s. So in before 1980s, there is a vendor lock-in, which organizations were forced to purchase all networking hardware and software from a single manufacturer. So they really have to choose which to purchase from, right? Like, for examples, it's sometimes confusing whether you want to purchase from IBM's Mtcna or Mtcna. It's too much. So there is also a closed system. So there was impossible for a machine from one manufacturer to communicate with another, as network protocols were proprietary. They're different, so they cannot communicate. There is also a monolithic design before 1980s. So networking software was often deeply integrated with the operating system, lacking a modular structure. So it's like a one pack thing. There is also a limited scalability, so you cannot scale it well. If you want to expand it more, it's kind of hard. And then there's the transition when it want to enter the 1980s. There is ARPANET, TCP/IP. The ARPANET is predecessor to the internet, introduced the first major open collaborative networking protocol, TCP/IP, in the late 1970s and early 1980s. And then after that, there is OSI development in 1977. The ISO began developing the OSI reference model to create a standardized 7-layer framework for and to foster open communication. Here you can see 1969 the ARPANET, and then there's 1980 NSFNet, and then we have what we have now, the internet, in 1990. Yeah. So after open networking models existed in the 90s, and now the introduction of open models, OSI and others, and mainly OSI, and subsequently the practical implementation of the TCP/IP suite transformed the industry. There is interoperability. Systems from different vendors could communicate seamlessly, eliminating vendor locked in and fostering a competitive market. There is also a modular architecture, so you could really layer the approach, allow developers to change one layer without replacing the entire system. There is also a standardization. Protocols became public, leading to rapid growth of the internet, like we are now. White box networking also, a modern open networking allows for the separation of hardware and software, where organizations can buy open source hardware and install their preferred network software. There is also the Industry 4.0 or SDN. The principles of open networking laid the groundwork for software-defined networking, SDN, allowing for greater programmability and centralized control. So let's go to the next one, shall we? The next one is TCP/IP model. So TCP/IP model is layered networking framework that explains how data is communicated between devices over the network using standardized protocols to ensure reliable and efficient transmission. Defined as a full-layer architecture consisting of application, transport, internet, and network access layer. As you could see here, there's only 4 layers in TCP/IP model, and TCP/IP model is standardized by RFC 1122, which specifies its structure and behavior. Simpler and more practical than 7-layer OSI models, because as you can see it's only 4 layers, not 7. and it serves as the core framework of the modern internet and networking system. So let's get in depth into the TCP/IP model. So the TCP/IP model, let's see here. The application layer, it's the first layer of the TCP/IP. The application layer includes the protocols used by most applications for providing user services or exchanging application data over the network connection established by the lower level protocols. These may include some basic network support services such as routing protocols and host configurations. Examples of application layer protocols include the Hypertext Transfer Protocol, or HTTP, as you may know now, and the File Transfer Protocol, or FTP. You can transfer files, and then there is the Simple Mail Transfer Protocol, and the Dynamic Host Configuration Protocol also, where you get IP automatically and data coded according to application layer protocols are encapsulated into transport layer protocols units such as TCP streams or UDP datagrams, which in turn use lower layer protocols to affect actual data. So if you guys don't know, we are going to learn encapsulation later, so we are just going to move on. The TCP/IP model does not consider the specifics of formatting and presenting data, and does not define additional layers between the application and transport layers as in the OSI model. According to TCP/IP model, such functions are the realm of libraries and application programming interfaces. The application layer in the TCP/IP model is often compared to a combination of the 5th, session, 6, and 7 layers of the OSI model. Application layer protocols are often associated with a particular client-server applications, and common service have well-known port numbers reserved by the Internet Assigned Numbers Authority, or as you may call it, IANA. For example, the Hypertext Transfer Protocol uses server port 80, and Telnet uses server port 23. Clients connecting to a service usually use ephemeral ports, i.e. port numbers assigned only for the duration of transaction at random, or from a specific range configured in the application. At the application layer, the TCP/IP model distinguishes between user protocols and support protocols. Support protocols that provide services to a system of network infrastructure. User protocols are used for actual user application. For example, FTP is a user protocol and DNS is a support protocol. Although the applications are usually aware of key qualities of the transport layer connection, such as the endpoint IP addresses and port numbers, application layer protocols generally treat the transport layer and lower protocols as black boxes, which provides a stable network connection across which to communicate. The transport layer and lower levels layer are unconcerned with the specifics of application layer protocol. Routers and switches do not typically examine and encapsulate traffic. Rather, they just provide a conduit for it. However, some firewall and bandwidth throttling applications use the packet inspection interpret application data. An example is the resource reservation protocol. It's also sometimes necessary for applications affected by NAT or to consider the application payload. So in conclusion, the top layer of TCP/IP model closest to the user, where application like web browser, email clients, and file sharing tools interact with the network. It provides an interface between user, software, and lower layers that handle data transmission, enabling seamless communication over the network. So TCP/IP in the application layer acts as a bridge between user application and lower network layers, support protocols such as HTTP, FTP, SMTP, and DNS, and also it handles data formatting so information is correctly understood by both sender and receiver, provides encryption for secure communication, manages sessions to track ongoing connections. And that's it for the application layer. Now next to the transport layer. Ensures reliable and efficiency delivery of data between devices, managing segmentation, ordering, and transmission as needed. So transport layer segmentation and assembly breaks large messages into packets and reassembles them at the destination. So they pack it into one message and then chop it up, chop the messages up, and then so they all reach the destination and then reassembles it, and then it's very reliable delivery and error handling TCP. So TCP checks for errors, resends lost data, and ensures correct order. So when they chop all the messages into packets, they check it again if the message is fully complete or it's not corrupted, of course, so there's no error. It's fast communication because you sending many things to one destination. So the UDP covers low latency connectionless delivery without error checking. And there is also flow control, prevents the receiver from being overwhelmed by regulating data flow, and multiplexing uses port numbers to allow multiple applications to share the network simultaneously. There's two in transport layer protocols. There's TCP and UDP, of course, as you can see it here. There's so TCP, when client syncs, the server acknowledges it and the client acknowledges back. When in UDP, the client requests response, so it's like whoosh, like you don't have to check it again, like so the TCP or transmission control protocol is used when reliability and accuracy are more important. It ensures that data is delivered exactly as it's sent. There is error checking, retransmission, order delivery, connection oriented, and use cases like loading web pages, downloading files, sending emails, or any application where data must be complete and accurate. As for UDP, it's only used when speed is more important than perfect accuracy. It is faster but does not guarantee reliable delivery. So in UDP there may be some packets that fall off, like if you use UDP to send a message, maybe they chop it up, chop the messages up into packets. When they deliver it, some of the packages lost and there's no checking back, like okay, corrupted message, boom. And there's no error checking, no retransmission, no order delivery, yet it's lightweight though. And use cases is live video streaming, online gaming, VIP calls, or real-time application where speed matters more than reliability. As you would see many things like video streaming. Video streaming, you see people like streamers sometimes lag a bit, and the data is very fast. It have to be real time. Sometimes it lags, sometimes it's false, sometimes it usual. And there is internet layer, where they are responsible for addressing, packaging, and routing data packets so they can travel across networks and reach the correct destination device. It ensures that data can move between different networks efficiently. There's logical addressing, packet routing, fragmentation, and reassembly. There is protocol support. Then next there is network access. Link layer responsible for physically transmitting data over network hardware, including cable, switches, and wireless connection. It handles how data is formatted for network medium and ensures it reaches the next device on the path. So there is a physical transmission, framing, error detection, MAC addressing, and access control in network access. So let's see the working of the TCP/IP model. So as you can see here, there's I have the diagram given below. So when sending data from sender to receiver, as you can see, there's a source, there's a destination. The application layer from the sending data, or from the sender, the user software. And then there's a transport layer. The data is broken up into segments, and TCP or UDP adds control information to ensure reliable delivery or fast transmission. And there's internet layer. Each segment is encapsulated into packets with IP addresses so it can be routed across network to the destination device. And there is the network access or link layer. The packets are converted into frames suitable for the physical network with Ethernet or Wi-Fi, and transmitted over cables or wireless signals. And then for the destination, when receiving the data in the network access layer, it's really the frames are received from physical medium and checked for errors. Internet layer frames are unpacked to extract packets and use the IP address to ensure it reaches the correct device. And then there's transport layer. Segments are reassembled into original message, and any missing corrupted data is corrected if TCP is used. Application layer. The complete data is delivered to the user application. Like as you can see here, this is source, destination. So all the layers are here. Messages, segments, or user datagrams, frames, they send through the router and then reach the destination, of course. So what is the advantage you could see from here? So the TCP/IP model is widely used, platform independent, reliable communication, scalable, and open standard. Yet the limitations are complexity for beginners, no strict layer enforcement, overhead, security limitation, and limited multimedia support. So let's go into the encapsulation and decapsulation, as if you are curious why am I saying encapsulation very like many times. So what in a In data communication, there are two concepts involved in transmission, namely encapsulation and decapsulation. Encapsulation adds, and decapsulation is the reverse process of encapsulation, so it like extracts the data. So if we can see here, if you can see there for encapsulation, it's like when you compress a data, but it's not really compressing, so it's just you putting a data into a container, and so wait, no, the best thing to describe this is like you want to send a container from one country to the other, and a container usually fits many stuff. As for in the network thing, there is actually data in the container. So encapsulation is where you store data to eventually it's ready to send. So it's going to make the transmission more smoother. And then there's the decapsulation part, where you are the other country, where you like open the data, extract it, and you get the data from the container. It's basically that, of course. As you can see here, this is the encapsulation part from application. Application is the data, and then in transport there is segment header that near the data. Then after, of course, it's like a train. Data, and then segment header, packet header, and then through the data link, frame header, and then after the data link, frame header and frame trailer are the front and back of the container, like where they complete it, and then they send through the physical like bits, and then the encapsulation, they from bottom back to the data. It's simple as that. Okay, let's go to the last one. It's OSI model, OSI, yeah. OSI, Open Systems Interconnection Model, is a conceptual framework that standardized how different computer systems communicate over a network, developed by International Organization for Standardization, ISO 1984. It breaks down network communication into 7 distinct layers, each with specific functions. Why does it matter? Of course, OSI most matters because it helps network engineers and developers understand how data travels from one computer to another by dividing communication into layers. It makes troubleshooting easier, allows different technologies to work together, and provides a common language for discussing networking concepts. It's like clearer. There is 7 layers, of course, as you can see here. So you still have to remember the application is the most near the sender, and the physical layer is to the receiver and back to it again to the application layer. So it's like whoop, so first thing first, physical layer, from the bottom, the lowest layer, dealing with the actual physical connection between devices like Ethernet cables, and other things. It handles raw transmission of raw binary data, zeros and ones, over physical media like cables, fiber optics, or radio waves. This layer defines things like voltages, levels, cable types, and connector shapes. There's data link layer. This layer takes the raw bits from physical layer and organizes them into frames. It handles error detection and correction for data transmitted over the physical link. There's network layer. The network layer is responsible for routing data between different networks. 4. Transport layer. The layer ensures reliable data transfer between systems, so it's going to be safe, of course. It breaks data into segments, manages flow control, and can provide error checking and recovery. So they provide many things. And if a connection is interrupted, the layer manages the dialogue between two computers. 6. Presentation layer. This layer acts as a translator, converting data between the format the application uses and the format needed for transmission. It handles encryption, decryption, compression, and data formatting. For example, it might convert JPEG image or encrypted HTTPS data into a format that can be transmitted. And then there is application layer. The topmost layer is where users and application interact with the network. So how is it work? How does it work? When you send data, it travels down through the layers on your device, gets transmitted across the network, then travels up through the layers and the receiving device. Each layer adds its own information. As data moves down and strips them off as data moves up, a process called encapsulation and decapsulation. For example, when you load a web page, the application layer handles the HTTP request. The transport layer breaks into TCP segments. The network layer adds IP addressing, the data link layer creates frames with MAC addresses, and finally the physical layer transmits the actual bits over the wire. So I think that's it for today's videos. Yeah. Okay, thank you for watching. See you next time again in the next video.